Today, let's look at relations that are defined by graphs and by equations. Since any point on the Cartesian coordinate system can be written as an ordered pair, and sets of ordered pairs define relations, any two-dimensional graph defines a relation via its points on the Cartesian coordinate system. The domain of a relation defined by a graph is the set of all the first coordinates or x coordinates for points on the graph, and the range is the set of all second coordinates or y coordinates for points on the graph. For example, this graph consists of the ordered pairs 5, 3, -4, -5, 0, 2, 2, 4, 4, 3, and 2, -4. So it associates 5 with 3, -4 with -5, 0 with 2, 2 with 4 and -4, and 4 with 3. The domain of this graph consists of all the first coordinates or x coordinates. So 5, -4, 0, 2, and 4. And the range of the relation defined by this graph consists of all the second coordinates or y coordinates. So 3, -5, 2, 4, and -4. This is a finite relation, meaning that there's a finite number of correspondences, and the domain and range are both finite as well. So we can also write it as a chart, and we can write it as an arrow diagram. Written as a chart of values, we get a row of the chart for each ordered pair with the domain elements on the left and the range elements on the right. So we have a row 5 is associated to 3, another row showing that -4 corresponds to -5, another row showing that 0 corresponds to 2, a row to show that 2 corresponds to 4, another that shows 4 corresponds to 3, and another that shows that 2 corresponds to -4, one row in the chart for each ordered pair that represents a point on the graph. To write this as an arrow diagram, we write all of the domain elements on one side and all the range elements on the other side, and then we have an arrow for each correspondence. So an arrow from 5 to 3, an arrow from -4 to -5, an arrow from 0 to 2, an arrow from 2 to 4, an arrow from 4 to 3, and an arrow from 2 to -4. And these are some of the things you can do with a finite relation that's defined by a graph. But not all relations have a finite number of correspondences or finite domain and range. This graph, for example, also defines a relation where there's a correspondence defined by every point on the graph. For example, this graph contains the point 4, 1, which means that in this relation, x equals 4 corresponds to y equals 1. It also defines via the point on the graph 1, 3, an association that says that x equals 1 corresponds to y equals 3. This point here, which is the point -1, 0, says that x equals -1 corresponds to y equals 0. And you get a correspondence like this for every point on the graph. This graph has infinitely many points on the graph. I picked a few where it's easy to see what the point is called, but there are many other points on this graph, infinitely many, say here, and here, and here, and many, many other points, and they all define a correspondence. Because this graph has infinitely many points, it has infinitely many correspondences, and we can't list them all out because there's just too many. So we can't really write this as a chart of values or as an arrow diagram. But it does define a relation, and we can talk about its domain and range. And it's going to turn out that relations defined by graphs in this way are very important in mathematics. The domain of a relation defined by a graph consists of all of the x coordinates for the points on the graph. So for a graph like this with infinitely many points, you can think of it as where the graph exists horizontally. If you look at this graph, you can see that the graph exists between x equals -3 and x equals 5. See, if you look in between -3 and 5, you've got graph in that area. However, if you look to the left of 3, there's no graph over there. And if you look to the right of 5, there's no graph over there. So that is not part of the domain. And the domain of this relation is the entire interval from x equals -3 to x equals 5. It includes the endpoint -3 because the point on the graph with x equal to -3 is included in the graph. And you can tell that because it has a closed circle. The circle is colored in. But the endpoint at 5 is not included in the domain because you see the point that would have x coordinate 5 on the graph has an open circle, a circle that is not colored in and is not included in the graph. So our domain is the interval -3 to 5 with -3 included, but 5 not included. You can think of the range as where the graph exists vertically. So if you look at this graph, you can see that you have at least some of the graph everywhere between y equals 3 and y equals -3. So if you look between -3 and 3 vertically, you've got graph in there. So that's all part of the range. But if you look above 3 or below -3, see, there's no graph up above 3 or below -3, so those values are not part of the range. So our range consists of the entire interval between y equals -3 and y equals 3. The endpoints 3 and -3 are both included because the points on the graph that will have y coordinates 3 and -3 are both part of the graph. For y equals -3, the point with y coordinate -3 is an endpoint of the graph with a closed circle to show it is included. And for the y coordinate 3, the point with that y coordinate is just one of the interior points in the graph. So our range is the interval from -3 to 3 with both endpoints included. Our domain and range can also be written using inequalities instead of interval notation. Just make sure you use the appropriate variable. Our domain, the interval where x is between -3 and 5, can be written as -3 is less than or equal to x, which is less than 5. And our range, y in the interval of -3 to 3, can be written as -3 is less than or equal to y, which is less than or equal to 3. A solution to an equation in two variables can also be written as an ordered pair. So any equation in two variables also defines a relation that consists of all of the ordered pairs that are solutions to the equation. The domain of a relation defined by an equation consists of all the first coordinates or x coordinates to solutions for the equation, and the range consists of all the second coordinates or y coordinates of solutions to the equation. And just like graphs often have infinitely many points, equations in two variables often have infinitely many solutions and define relations that we can't really list all the correspondences to write them as a chart or a list of ordered pairs or as an arrow diagram. But they do define relations, and we can talk about their domain and range. For example, the equation x is equal to y squared is an equation in two variables, so it defines a relation. The relation defined by this equation associates x equals 0 to y equals 0 because the point 0, 0 is a solution to the equation. It associates x equals 1 to y equals 1 because 1, 1 is a solution to the equation. Or x equals 4 to y equals -2 because the point 4, -2 is a solution to the equation x equals y squared. And there are infinitely many more solutions to this equation, so there are infinitely many more correspondences defined by it. The domain of this equation turns out to consist of all the non-negative numbers. And the reason you don't get negative numbers as part of the domain here is because y squared can only be 0 or positive. It cannot be negative. So x cannot be negative. So the domain, all the possible x's that could be a solution to this equation, is the numbers that are not negative. However, you can square any number. So the range turns out to be all real numbers, or the interval from -infinity to infinity. This is actually a lot easier to see from the graph, which is frequently the case. Here is the graph of the equation x equals y squared, and we can see looking at this graph horizontally, there is no part of this graph over here to the left of 0. Starting up here, it goes to the left, to the left, to the left till it hits 0, and then it turns around and starts going back to the right and does not ever hit any of these points below 0. So the domain is everything starting from 0 and going up to the right and continuing on in that direction forever. So that is the interval 0 to infinity, which we can write using inequality notation as 0 is less than or equal to x is less than infinity. Looking at this graph vertically, we see that our graph is going upward forever over here, and it goes down to hit 0, and then it continues going downward, and it actually continues going downward forever, and every real number is a possible value for y. So looking at this as an interval, we see that our range is the interval that consists of all real numbers y from -infinity to infinity. And we can write that either as the interval -infinity to infinity, or using inequality notation as the statement -infinity is less than y, which is less than infinity. So now you've seen a couple examples of how a graph or an equation defines a relation and how you might think of domain and range in those contexts.